Welcome back. Today we're going to get into a few other topics when it's concerning performance. So we're going to get away from the engine type things. In the previous video I mentioned that you can actually find more performance within your running car when you actually pay attention more to the drive line than you actually do by adding power to the engine. Now realize in previous videos I also mentioned that if you have a final goal, it's best to reverse engineer things. So starting with the actual tires to match the performance that you're trying to get to, whether it's drag racing, circle track, street racing, so on and so forth. The rims, believe it or not, they are also part of the equation to reverse engineering. You're if you're going to a wider tire for drag racing, are you going to a center mounted with back spacing that places the mounting flanges of the rims to the axle so that it distributes the weight equally across the pad of the tire? Or if you're using a deep dish, if you're trying to look for that Pro Street look with a narrowed rear end in order to fit the bigger tires underneath the car. So first of all, reverse engineering, getting everything ready for the engine. Now, typically, when it comes to circle track racing, individuals are trying to work within the rules. Obviously, drag racing has also the same kind of class rules, the size of the tires, so on and so forth. But the drive line is open to modifications. There's unlimited amounts of rules out there for the engine itself, the components that can be added onto it, the modifications, so on and so forth. But the drive line is basically up to the builder within their pocketbooks of what they can afford and the amount of attention that's given to the components to modify them. So we have to be very clear. We're going to go through this list. In the next few videos, we're going to cover wheels and tires, hubs and bearings, because there is a difference, especially within circle track racing. When you start looking at the super late model, or even some of the sprint car automobiles, they all have different hubs and bearings, both for the front and rear tires, or the coaster or drive wheels. They also have different brakes. Everybody knows the difference between a disc brake or a drum brake type system. There's even more discussion about the size of the brakes in order to stop a vehicle in circle track racing. The brakes are normally larger in diameter. They're normally designed with lighter weight. Some of your high-end drag racers have adopted circle track racing brakes onto their drag cars, using materials like carbon fiber rotors to drilled and relieved rotors to lighten the weight, all the rotating mass. You realize no matter what your engine is creating within power, if you can lighten up everything behind it, you're actually getting more of that power to the ground to accelerate the vehicle. We're going to get into the bearings, because again, some of your late model, super late model, they're using the larger aluminum hubs, which incorporate much larger bearings that are also spread apart farther than to rely on the single axle bearing that is typically on a daily driver or a solid axle or independent type suspension for a street vehicle. Realizing that the intention for circle track racing is to go around corners, and the amount of G-forces that are exposed to the axle ends and within the hubs is different than if you're driving down the road, having to deal with the potholes and so on and so forth on an even surface, to cars that are off-road use, four-wheel drive trucks, that source. All of them have a different hub design. We're getting into the actual axles themselves, whether they have been lightened up, gun drilled, so on and so forth. Again, in drag racing, you're looking for an axle that's going to be able to withstand the twist of the initial hit of the power being released into the drive line to accelerate the car. Where circle track racing, you're already moving, and the actual weight of the axle can be the determining factor if it can actually accelerate or not. So you can't necessarily take circle track axles and put them in a drag car and expect them to survive. But you don't want to take drag racing axles, put them into a circle track car and expect them to lighten up. Normally they're a larger diameter. When it comes down to the spline, normally they're a higher count spline with finer splines, where drag racing is going to be a little bit bigger teeth and a lower count. For instance, most of your 4 9-inch Chrysler 8 3/4 to the GM 12 bolt, they're going to use somewhere between that 25 spline up to a 40 spline. Again, with a larger diameter axle. Okay, so circle track racing with a lighter axle, they still use a 40 spline, but the axle is actually larger in diameter. So the splines themselves are actually smaller, but the axle is larger, so they don't have as deep a teeth. We're going to get into the actual carrier groups and gears. Circle track racing, once again, typically open rear ends are used for your intermediate entry level type racing. But once you start getting into super stocks or late models, they are a spooled rear end. Drag racing, most of your vehicles out there have some kind of an anti-slip system or a spool to combine both of the rear tires to turn in the exact same ratio. Now, going in a straight line, having those tires locked up is a benefit to you. So things like air pressure and how hard you launch can actually change the diameter of the tire and actually cause the vehicle to turn when it's trying to go in a straight line. Circle track racing is similar to that, to where when you're going around a banked embankment or a corner, all the G-forces are shifting the tire to one direction, and the height or the air pressure within the tire can change the diameter of the tire to help the car actually move. So it's the rotation of the tire. With having an outside tire a larger diameter than the inside tire, it will naturally give that turning motion, even though the axles and the rear tires are actually combined as one. We're also going to get into that, I forgot to write up on the board, with the different axle types, which we'll also get into. We're going to be talking about the factory vehicle, your everyday driver type axles, like the 4 9-inch 12 GM 12 bolt to the Chrysler 8 3/4 inch. We're also going to be talking about the Winters type axles that are free floating, and they're constructed a little bit different. That is actually the oldest design of axles. That is what the Ford Model A actually used, was a floating rear axle. So we're going to be talking about the axles themselves, what's more apparent, and what it takes more energy to actually turn. We're going to get into drive shafts. Obviously, drive shafts come in different materials, whether it be steel, aluminum, or a composite. There are Kevlar, carbon fiber, so on and so forth, within the drive shafts, and they will be mounted on the cars for their intended use. You're not going to take a carbon fiber drive shaft and put it on a car that is releasing the energy from a trans brake. You would shatter the actual drive shaft. Aluminum can take the impact and twist, but in order to make something out of aluminum, you have to make it larger in diameter to have the same strength as a steel or a chromoly. So circle track racing, once again, it's not to handle that abrupt power that's going into it. It's to lighten the whole entire rotating mass so that more power actually makes it to the rear tires. We're going to get into the actual transmissions, and we're going to start out with that a little bit here today. I have a piece of homework for you guys to do to understand the difference between a manual and an automatic transmission and how much power is robbed in an automatic transmission. Okay, so we'll get to that. We're going to go into the actual clutch and flywheel combination for a manual transmission compared to a torque converter. The mechanical to the hydraulic multiplication that comes from a torque converter. Now, it's the reason why it's called a torque converter is it's converting mechanical centrifugal force of the outside drum of the torque converter. The fluid, the transmission fluid inside the torque converter, is then passing over the stator. So we're going to start out in that at the bottom of the list. We might jump around a little bit as we're discussing it because there's different examples I can give to you to help you understand how things work. Now, with the torque converter, if you can imagine being in an airplane, a propeller-driven airplane, the actual pitch of the propellers of the airplane can actually change pitch as the engine is increased in RPM, given more power, and the pitch will be more aggressive to grab more of the wind and push it. Once the airplane is up in the air and it's at its cruising speed, the efficiency can be turned down to where the props can be lifted a little bit to give it a cleaner cut through the air to sustain whatever airspeed they're trying to maintain. A torque converter works similar with the stator, but instead of being able to adjust it, they're fixed. So the stall speed of the torque converter is dependent on how many fins, the angle of the fins, and how the fluid is then driven over the stator and how aggressive those designs are. That's going to determine the slip that the torque converter can actually spin before overriding the stator, and how much the stator then picks up as RPM increases. So any of you automatic transmission gurus out there, let's say you're from Hughes, or excuse me, not Hughes, Hudges, you can call in and give them the amount of horsepower that your engine is outputting, and they have a general idea of the design of the torque converter that it's going to take to actually transfer that power into the transmission. Now, they have obviously years of experience, multiple customers that have used their torque converters, and they obviously look for reviews to see if it's fit the circumstance, so on and so forth. But if you change one thing on the car, say that you're introducing something as simple as nitrous oxide, you put a plate system on there, now the torque converter has to be modified to be able to handle that immediate release of power from the engine that's different from the natural aspiration. So torque converters, the design of the internal fins and how many fins there are, the angle they're at, the diameter of the actual, the drum of the torque converter, all of that is a specific science. Now, realizing the mechanical transformation from mechanical power into hydraulic power then turns back into mechanical power through the stator into the actual transmission. Now, transmissions, automatic transmissions, this is where we're going to get into your homework. I want you to take out it's warm enough out that you probably have a jug at home that you're mixing maybe some of your Kool-Aid in, or some lemonade, so on and so forth. I want you to take the empty container with your stir spoon, and with an empty container, I want you to spin the spoon around as fast as you possibly can with your hand. There's very little resistance. Now go ahead and mix your favorite drink and do the exact same thing. Put the spoon in with your liquid and rotate the spoon, mixing spoon as fast as you possibly can. You will feel that resistance within your hand. That is the type of resistance that an automatic transmission introduces into the power robbing of the power the engine produces. So I'm just going to throw these numbers out here. It's not going to be exact. Say you have a 400 horsepower engine and you put a turbo 350 transmission behind it, or equivalent from any one of the other manufacturers, C4 or Chrysler's Variation, so on and so forth, 727, whatever. You realize that it's mechanical to hydraulic multiplication within the torque converter. That's exactly what it does. It's a torque multiplier. Because you're using a larger drum of the torque converter and putting it to the smaller diameter stator. You are then driving it into the pump, which circulates the transmission fluid through the rest of the automatic transmission, engaging or disengaging all the different clutch packs, and the timing through the valve body of when those clutch packs actually engage, so on and so forth. Most of your automatic transmissions, as the name states, it is able to do it under its own pressure. So as pressures increase and the RPM of the pump increase, the transmission engages different clutch packs, and those clutch packs are then also connected to different gear ratios. So you'll want to pay attention. I actually have a multi-speed bike right behind the camera. So if you can think of your 18-speed bicycle that you might be riding, typically the front sprocket has 3 different gears and the back has 6, and they are all of different diameter. Each one gives a different final gear ratio. You can realize that if you put it on the smallest sprocket with your feet and the largest sprocket in the back, you can pull wheelies and you'll have all kinds of torque. but you run out of acceleration fairly fast because the horsepower, the revolution cannot increase much more. It has exceeded its efficiency. We're on the opposite end of the spectrum. If you put it on the largest sprocket of the bicycle in the front and the smallest at the rear, you can't barely pedal the bike. Okay, even though your legs, say that your legs is the horsepower being created by the engine. The gear ratio can determine when the power can actually be put to use through the gear ratios. So understanding gear ratios will also allow you to understand when in the race, whether it be in a straight line of a drag race or within a circle track situation, when the power is actually going to be shown through the most. So for instance, I'm going to use the example that we learned this year. We got a brand new chassis. We're still using the same Ford engine plant that we've had the last couple of years. We're producing about 445 horsepower. Now, because it's a new chassis, it's a little bit more aerodynamic, which doesn't really matter when most of your races are underneath 120 miles an hour. The weight placement is a little bit different. Areas that you can mount it to help balance the car out. Now, this year what we learned is that even though we're producing the same amount of power, this year's chassis, when we come out of the corners, get on the gas, our engine was able to overpower the tires and actually cause the back end to slide out. So we're overpowering the tires. So in order to adjust when the power comes in, we need to actually increase the gear ratio. So we're at 513, so we're actually dropping down to a 480-ish. So that means that the power is being delayed. More from the get-go, coming out of the corner, overpowering the tires, where we get more of the acceleration later once we get into the straightaway, and it'll carry farther going into the next corner. So just a little difference of changing gear ratio can actually determine when the power comes on. Now, obviously, through an automobile using a transmission, the automatic transmission in a typical muscle car has 3 speeds. Even an overdrive transmission, it is not necessarily an additional gear. It is locking the torque converter to where the outside drum of the torque converter is spinning at the exact same rate and being transferred that revolution into the stator. So the main drive shaft into the transmission is locked 1-to-1 to the actual spinning revolutions or RPM of the flywheel, or excuse me, sorry, brain fart here. Obviously, the torque converter is not connected to a flywheel as in a 4-speed mechanical clutch type system. It's slipping my mind. I'll think about it in a second, but remember that every one of those gear ratios is determining when the power is maximum being delivered into the next part of the driveline. So again, first gear on most transmissions is going to be fairly low. It's going to be that grainy gear to allow it to accelerate the weight of the car. But the lighter the weight of the car, the more gear ratio you can actually grow it to the point where you don't have to depend on that grainy gear. You can step up the gear ratio a little bit more and delay when the power is actually going to the rear wheels. So as I mentioned, taking my circle track car and converting it into a drag racing car, I skipped using first gear whatsoever. I was actually launching from second gear, which has a quite a bit different gear ratio. In order to transfer the 8th mile, I would only need 2 gears. I don't need all 4. Now, with an automatic transmission on most muscle cars, there are 3 speeds. But if you actually look at an automatic transmission in an 8th mile car, what are they doing to the gears? Okay, first gear, they're running through first gear pretty much by the time they've gotten through the traps of the lights. Okay, so by the time they've reached the 60-foot mark, the car is already going into second gear. They have utilized the maximum torque multiplication that the engine can do through the RPM range to the point where in order to accelerate more, it has to shift. So again, the 60-foot area of the track is not only to measure how fast you can get there, but the timing of when the transmission is actually shifting from first to second, whether that's through a manual valve body or shifting the gears even with a manual transmission. Where are you actually shifting into second gear? If you're crossing the 60-foot line and you're still at say 4 or 4,500 RPM, you can start cheating up your gear ratio quite a bit more to maximize your 60-foot times. But remember that at the end of a drag strip, you also have to remember what you're crossing the traps at the end of the racetrack. Circle track racing is a little easier as far as that you know a general idea of where you're going to be. Depending on the other racers in your car, in the corners you might be dropping down as slow as like 80 miles an hour, where in the straightaways you could be approaching 120. It's a one gear or 1 RPM range. You're not necessarily shifting down to third in order to accelerate out of the corners. You're allowing the car to accelerate in its 4th gear. The final gear ratio for many transmissions is 1:1. So for 1 evolution to be put in, it is 1 revolution coming out of the tail shaft of the transmission. Now obviously you have your gear ratio in the rear axle that also does torque multiplication. So the higher the gear ratio, the more torque it can actually transfer onto the tires. So for any of you one-wheel wonder cars out there, you'll realize if you go from your 308 gear ratio to a high 480s or something like that, you can just barely tap the gas and you'll spin the tires, because the torque multiplication through the gear ratio is modified. It's multiplied from what the engine can actually output. So as I said in the last video, you can have that 350 horsepower engine, but if you concentrate on the gear ratios of the driveline and modify or change them, you will actually feel more of the performance in the seat of the pants and in your results in the race than by actually adding more power to the engine. Let me see if I can come up with even a better example of that. Let me see. I'm going to grab something real quick. All right, so what I have here is one of our projects we're working on right now. We're rebuilding a mini bike. This is the engine that was put into a mini bike that I actually got from Dick Trickle, one of my first jobs. So the mini bike did not have an engine when I bought it, or earned it, excuse me. I didn't pay any money for it. I actually earned it by working in a shop. And then I found this little mini crotch rocket engine, a little 50cc. Now the transmission on it, any of these is a centrifugal force. So the more RPM there is within the crankshaft rotation, that is transferred into a clutch system, and the clutch system engages with more RPM. That then goes to the final drive, and the gear ratio goes into your sprockets. Now, if you were to change a sprocket, this is approximately a 2-inch sprocket right now. If you were to change this to a 3-inch sprocket without changing anything else on the mini bike, you're not going to accelerate as fast, but your top speed is going to increase. Okay, so from a 1-inch to a 2-inch, let's say that you're doing top speed of 10 miles an hour with a 1-inch. The 2-inch you're going to be at about 20 miles an hour. With the 3-inch you're going to be about 30 miles an hour. That's just a roundabout figure. That same thing is going to transfer to the gear ratio, final gear ratio within an automobile. Realize this doesn't have a transmission with 3 multiple gears. It's just moving the power from the clutch pack to one main large gear, and then that gear is then transferred down to a smaller gear for torque multiplication. So small to big, going back to the bicycle. If you have it on the small sprocket on the front and go to the big one in the back, you have all kinds of torque. Where if you use the large sprocket at the front crank and the small one at the rear, you're not going to have a lot of acceleration, but you're going to have the top speed. And the trick with bicycles or circle track cars is to match the amount of output through the gear ratios. So even though your restrictions of the engines are limited to compression, components that you can equip the engine on, cubic inch, so on and so forth. Even an engine that's only making 350 horsepower in the stock class, from 60 miles an hour to 100 miles an hour, it would out accelerate a drag car. Okay? In final gear, it would actually out accelerate a drag car in that time frame. It's because it's being designed around that miles per hour and RPM range. Where a drag racing car, you're going from a dead stop, utilizing torque to accelerate the car, and then the horsepower to carry it through. Now, the practice commonly today is that even drag cars are starting to concentrate on that higher RPM range. So stall speeds or torque reverse stall speeds, or even hand braking type systems, to where they're launching at 5,000 RPM and they might have a red line of 7,000. They're only utilizing the wind up stored energy of the engine. So even in that case, if they're making 500 horsepower, they're only using 2,000 RPM of that being transferred into the driveline. Now at 2,000 RPM, where's normally the torque curve in the power graphs? They've dropped off way before that, correct? It is the efficiency of the torque, the amount of torque being created, and the RPMs. Okay, so by releasing the transmission, say at 5,000 RPM, you're not utilizing the maximum amount of torque that the engine actually can produce. You're utilizing the horsepower. So in previous videos I mentioned, if you're the type of do-it-yourselfer that you're building something that can be driven on the street and go to the track, you'll hear the ratios of, oh, I got something that's 80% street or 20% track. Obviously, the majority of the time you're going to be on the street. So you want to have gearing that you are going to be able to drive around at speeds of 25 miles an hour in the city, or 55 miles an hour on a country road, or 70 miles an hour on an interstate, and be able to live with it, not winding the engine out so much that it overheats, wears down parts, so on and so forth. You're going to be utilizing the entire power band of the engine, from idle all the way to cruising speed or passing speed. That's the RPM that you need to concentrate on. The other 20% of the time at the track, you might introduce things that are a little bit more high performance again. Having that higher stall converter to where when you get on it, the torque converter can actually slip. So it delays the RPM of when it's actually transferring the power through the transmission. If you have a 5,000 stall torque converter at, say, 70 miles an hour on the interstate, you're going to be doing damage. Okay, simple as that. So again, going back, get a little off track as far as the engines, but through these series, we're going to be talking about each one of these. I'm going to be breaking them down. Why circle track drive lines, the way they're designed compared to what it is for drag racing, and street racing is actually a combination of both. Okay, so some of the things that we learned from circle track racing can be adapted into a performance street car. I'm going to end the video with this. Folks, we have to realize that for 50, 60 years, something that I had posted in a previous video, most of the technology that we have in our daily drivers has originated from racing. So here's a good example. The Ford variation of front suspension, the strut suspension, that was actually something that came from off-road Baja racing back in the 1930s. Okay, it was figured to be a lighter, more economical way to create a front suspension, to lighten it up so that the compression and rebound of the front suspension is not carrying as much weight. With a General Motors A-arm system, there's more weight actually at the knuckle going up and down, so that the spring or shocks have to absorb to adjust to keep the tire planted on the ground. We have found both in circle track racing and drag racing that the front suspension of choice is actually a strut front suspension, because it allows the suspension the most amount of travel and the lightest amount of suspension components. It's eliminating basically the upper control arms for the suspension. The actual strut becomes the upper control arm, while it is also the shock absorber and carries the spring. So everything is designed around lightening it up to increase the performance, especially when it comes to the driveline or the suspension. Now, I said I was going to close it out with that. This is what the videos are going to be curtailing for the next couple of videos. Again, it's something that is learned over time. Okay, so I'm glad somebody requested this kind of information. It's something that I might not have all the components on hand here, but it's something that we can share and talk about, because no matter what you're building, you can take advantage of some of these modifications. So depending on how much money you have, if you decide to turn to the aftermarket, there's also things that you can do with the original equipment. I'm going to leave you with this, with an example. Between the Ford 9-inch and the Chrysler 12-bolt or the Chrysler 8 3/4 inch, which one, because of the place of the pinion and ring gear, which one actually has the most efficiency? Which one actually takes less power to turn and actually convert that power to the axles? Some of you might think it's the Ford 9-inch. The reason why the Ford 9-inch is so popular is because of the ease of changing the gears. Obviously, you just have to take out the entire carrier group with the front cover, and you can change gears fairly quick. Ford was also one of the first ones that came out with the C-clip eliminator type axle, so you didn't have to deal with any of that stuff. They were a little bit stronger. So all you had to do is slip out the axles enough to actually take the carrier out. You can change gears, put it right back in, slide your axles in and bolt them on the ends. You don't have to worry about the C-clip inside, which is actually a weak point in the GM or Chrysler configurations. Lo and behold, out of the 3 muscle car axle designs, between the Ford 9-inch, the Chrysler 8 3/4 inch to the GM 12-bolt, the GM 12-bolt actually has the most efficient design. It's not as friendly to gear changes, but if you already know what gear you're going to stay with, and that's it, install one and done, the GM 12-bolt is actually the most efficient axle out there. Even to the point where some of your top-end, top-fuel dragsters, which we'll be getting in here in a little bit, they have exchanged for the 9-inch design to actually go to the 12-bolt design. So if you are interested in that, you can contact like Mosier, Strange Axles, so on and so forth, and look what they have for their top-end designs. The GM 12-bolt design, or even used in heavier equipment, like 2.5-ton trucks, they are utilizing the 12-bolt design. Once you start going to 10 bolts or 8.5 or 8.8s from Ford, the strength goes down considerably. Those are axles meant to be used with factory equipment. Once you start modifying things, you have to look to the aftermarket, because the factory equipment won't handle the additional power that you might be introducing. So with that, I'll let you guys go. We'll be back, and I'll start going on to the next. Next video we'll be talking about the tires and wheels compared to circle track, to drag racing, to street cars, what they're exposed to, the different kinds, the materials, so on and so forth. We'll see you then.